So looking at one last example of related rates. This one is a little bit different from the others, but following the same principles of related rates problems in applications of derivatives, we can solve this problem just the same by saturating the details and the context into our just math model. So let's take a look at this problem. Light on the ground 50 feet from a wall. So we're going to have a wall, and we're going to have the ground. So 50 feet from a wall shines on a 5-foot tall man walking to the wall at 2 feet per second. At what rate is his shadow decreasing when he is 10 feet from the wall? Okay, so light on the ground 50 feet from a wall. So here's the light. 50 feet from the wall. So it shines on a 5-foot tall man. So here's our 5-foot tall man. It shines his shadow onto the wall. Here's the wall is really, really, really tall, negligibly tall. All right. So let's put some variables in here so we can use it to solve for derivatives. Well, we're asking for the rate of his shadow decreasing. So here's his shadow. So let's call that y. And we know that he's walking to the wall at 2 feet per second. So let's denote this distance, x, and this distance, 50 minus x. So we see that there's two similar triangles. Well, how do all these variables relate? Well, if he's walking to the wall at 2 feet per second, we can call this x, we can call that dx dt. So then to relate all these variables together, we see that this is a giant similar triangle inside an even bigger one. So 5 over y equals x over 50 minus x. Oh, excuse me, x over 50. So we have now an expression for x and y. Well, we know that y just equals 250 over x is 250 times x to the negative 1. So the change in y, dy dt, is going to be negative 250 x to the negative 2 dx dt. Well, let's go ahead and plug in dx dt because we know that the man is walking to the wall at 2 feet per second. So x is changing at a rate of 2 feet per second, which is dx dt. So this expression becomes negative 250 times x to the negative 2 times 2, which equals negative 500 over x squared. So now we have this expression for dy dt and x squared, and we're looking for the rate at which his shadow is decreasing. So we're looking for a dy dt. This is what we're looking for. So all we need is to find x. So what is x? So to solve for x, when the shadow is decreasing, when he is 10 feet from the wall, what rate is this shadow decreasing? Well, at 10 feet, here's your hint. This is your x. They're always going to give you either what you need to solve the problem or enough information to help you solve for what you need. So here they're giving you 10 feet, which is x. So let's solve for dy dt equals negative 500 over 10 squared, which equals Well, actually, x is not what they're giving you. So here it's a little tricky. 10 feet from the wall, well, 50 minus x is 10 feet from the wall. So actually, 10 feet is 50 minus x. So we'll have to do a little bit of arithmetic to get x. So 50 minus x equals 10. Then x equals 40. So then here we have negative 500 over 40 squared, which means negative 5 over 16 feet per second. So for this problem, we had to do a little bit of manipulation to get what we wanted. To review, we started with the relationship of the man's shadow casted on the wall. So we have a y term, we have an x term, and we're looking for the change respect to time of those variables. And we're looking for the rate of his shadow, so that's dy dt. And we solve for all the other variables based on the information given. So once again, for related rates problem, we have to just be very, very organized and keep in mind of the giant picture to get the answer that we are looking for. So thanks for watching Educator.com. We'll see you in the next lesson.